Hey, this is Mr. Wakefield again. We're starting chapter 5 right now, and in 5.1 and also in 5.2, we're going to be looking at not just equations, but systems of equations. So let's talk about what that means. We're going to start out with the most simple type of system, as we call it, and it is when you have two linear equations that both have two variables in them. All right, in the next section, we'll see sometimes 3 or even 4 equations occasionally, and we'll also see some problems that'll have 3 or maybe even 4 variables. All right, but if you have both 2 equations and 2 variables, 2 linear equations in particular, then what we do here in this section right here, 5.1, will show us how to solve that system. Before I get into how to solve it, what does it mean? What does the solution mean? What is the purpose of it? What are we actually finding when we find the solution? Well, let me just remind you first of all that when you have a linear equation in 2 variables, and in these problems we'll have a couple of them, but each one of those linear equations that has 2 variables in it is just like back in chapter 2 when we graph lines. Anytime you got a linear equation with 2 variables in it, it ends up becoming a line. Let me remind you that any graph, whether it's a line, a parabola, a circle, whatever it may be, all right, the graph is an illustration of all of the solutions to the equation. Okay, so every single point on the line here, for example, is a solution. This is going to be important here to understand what's going on. Okay, so here's the thing. When you solve a system, you are looking for all of the solutions that are actually solutions to both equations and only both. Okay, we do not want to just know the solutions to the first one. We do not want to just know the solutions to the second one. We want to know only the solutions to both. Okay, so if, for example, 3 comma 5 is a solution to only the first one, we don't care about that. We only care about the ones that are solutions to both. So since these are both linear equations with 2 variables, they represent lines. Now, I'm not going to be graphing when I do these problems, but if I show you the graphs, it'll help you understand how the whole process works and the whole purpose of it a little bit better. So you don't have to write down these graphs that I'm about ready to do, but again, it'll just be a good visual to help you understand what's going on. It'll get us off to a good start here in chapter 5. So I'm just going to pretend, I don't know off the top of my head what these graphs look like, but I do know that they are both lines. So let's just pretend like the first line looks something like this. Okay, and let's pretend like the second line right there, if I were to graph the second equation, let's just pretend it looked something like that right there. So every single point on the first line is a solution to the first equation. Remember, the graph is an illustration of all the solutions. So all the solutions to the first equation are on this line. All the solutions to the second equation are on this line. Okay? Are there any solutions that are actually solutions to both equations in that picture that you see right there? Okay? Well, there's only one point that is a solution to both, and it is the intersection point. Why? It's because the intersection point is the only point where it's the only point that's on both lines. All right, and if it's on both lines, that means that it is a solution to both equations. Remember, when we solve a system, as the directions say here, we are looking for whatever makes both of the equations true, whatever solution makes them both true. So only points that are on both lines are going to work. Okay, so again, you don't have to graph these problems, but this at least gives you a good visual of what's going on, though. All right, so most of your problems when you have the 2 variable, 2 equation systems, like we do here, 2 equations with 2 variables, x and y, okay, most of those problems will have just one solution because you're usually going to have one intersection point. But there are a couple other possibilities that we're going to run into. What if, let's say, for example, I had a system, and even though we're not graphing, just from a visual perspective, let's say that the 2 lines that the 2 equations represent, if I were to graph them, let's say that they ended up being parallel. Okay, what does parallel mean again? It means that the two lines are equal distant from each other, okay? They're the same distance apart from one end to the other right here. They never get closer to each other and they never get further apart from each other. They're the same distance away from each other from one end to the other. How many intersection points do parallel lines have? None, right? Okay, so up here we have one solution. All right, here we got no solution. As we talked about in the past, you guys, if you're solving something, whether it's just one equation or if it's a system, if you have no solution, you need to say those two words, no solution, and circle that. Okay, we'll get to an example of that here coming up. But that is another possibility. And believe it or not, there's actually one more possibility. What if we have two equations that look different, but they actually represent the same line, okay? Like, for example, let's say that you graphed the first equation, all right, and it looked like this. And then let's say you graph the second equation, it ended up being the same exact line. One line right on top of the other here. How many intersection points do you have when one line is right on top of the other? Okay, every single point on the line is an intersection point, right? In other words, every single point is a solution to both equations, all right, because every single point is an intersection point. So this is a situation where you have an infinite number of solutions because there's an infinite number of points on each line, and each point is an intersection point, and therefore it's a solution. So we have three different possibilities. And again, I want to make this really clear. I'm not talking about the next section, you guys. I'm talking about only when you have two equations and two variables. Okay? Not those bigger ones that we're going to see in the next section with 3 or 4 equations or 3 or 4 variables, something like that. No. Just this. Just in this situation, we've got these three different possibilities. Right? Again, most of the time it'll be this one, but occasionally it'll be one of these two. All right, so how do we find this out? Well, you might be wondering, well, why don't we just graph it all the time then, since we've already talked about how that all works and everything. The problem is that graphs are not always perfect, all right? When we draw, our lines are not necessarily perfect, and since we want exact answers, all right, we don't want to worry about the fact that the lines might be slightly crooked, all right? Or even if they are perfectly straight and everything, sometimes it's still hard to see exactly what the point is, where it intersects. Okay, sometimes it's hard to see if it's parallel. There's ways to figure that out, all right? Don't get me wrong, but these two methods I've got right here for you are better. They're easier, and you do need to learn both of them, all right, for the exam. When we eventually take the exam on this section, there could potentially, I'm not sure yet, there could be potentially a problem where you must use the substitution method. All right, just kind of like what it says here, where it says solve each system by substitution. It doesn't give you the choice. You have to use the substitution method. There could be a problem on the test just like this. And then there could be a problem on the exam where you must use the second method here. The textbook calls this the addition method, but I like to call it the elimination method. Some textbooks call it that as well. You could call it either one. All right, I believe the textbook calls it that. I'd have to check on that, but either way, whether they call it the addition method or the elimination method, the method is the same, and that's what's important for you to realize. Okay, so what are these two methods, you guys? Let's start out with substitution, as the directions tell us to do down here. The substitution method says these 5 steps right here. It says choose one of the equations, your choice, and then solve for one of the variables in that equation. In other words, get that variable by itself. So we have 4 choices here. I could get any one of these 4 variables by itself. Any one, your choice. So with that in mind, what would be easiest? Well, remember something, you guys. If you try to get the 2 by if you try to get this x by itself, you'd have to divide by 2. It's probably going to create some fractions. If you try to get this x up here by itself, you're going to eventually have to divide by 4. Again, it's probably going to create some fractions. Same thing here with this y up here. If you're going to have to divide by -5. Again, same thing. This one right here, you don't have to divide because the coefficient is 1. So when you get the y term by itself, all right, you don't need to do the division step. If you're not quite seeing that right here, let me remind you of how that works. All right. Anytime you got a linear equation, which this is, all right, both sides are polynomials, all right, normal monomial terms, all right, either being added together or just a single term, either way. Both sides are polynomials, and the highest degree of any term is 1. X to the first, y to the first. There's no x squareds or y squareds or anything. Again, that makes it linear, right? Pardon me, I know I've said that a million times this semester, but want to really make sure we know the method, know what we have, so we pick the right method to get the variable by itself. If you do have a linear equation and you have no parentheses, what do? You identify the terms that have the variable in it that you're trying to get by itself, and then you identify the ones that don't have the variable in it that you're trying to get by itself. If there's no parentheses in there, then you add or subtract the green ones over to the same side, but the opposite side of where the red one was. It doesn't matter what order you put these two terms in this case. We're not doing those mx plus b problems this time, so it's not as important. But I got y by itself, didn't I? Normally at this point, after you get the red term by itself, you got to divide out to get the y by itself. But it already is by itself. And so we are now done with step 1. Okay, it said to get one of the variables by itself. In other words, solve for it. We did it. Okay, so here's the very important second step here. It says substitute for that variable. In other words, take that equation and substitute it into the other equation. Do not plug it back into the same equation that it came from. Don't plug this thing back into here. Now, what do I mean by substituting into the other equation? What you do is you take the variable that's by itself, okay, that you got by itself in the first step. You take what it's equal to, and you replace that same variable up here with 5 minus 2x. Let's try that. Always use parentheses when you're plugging into something, whenever you're plugging into a variable. Okay? And I put the 5 minus 2x in there because that's equal to y, and so I replace the y in the other equation with that. Okay? So you always plug it into the other equation in step 2. What I've now created is I've created a one-variable equation. A one-variable linear equation. If you do this step correctly, it will always be not only a one-variable equation, but it'll be a linear equation. And right at the beginning of the semester, we reviewed about how to, and we've reviewed how to do one-variable linear equations, and we've done them on a number of occasions since then as well. What do? We distribute first. If there's any parentheses, which there are, then we combine like terms. Then we move over the terms that do not have the variables in it to one side. Just so long as the term that does have the variable in it is on the other. So go ahead and just keep the x term on the left-hand side and move the 25 over with the negative 11 so that the x term will be on the opposite side of the constant terms, which combine together to be 14. Then we divide out, and finally we have solved for x. But remember, from the picture I showed you, our answers are what? Our answers are the intersection points. The intersection points, key word there, points. All right, that means it's got an x and a y there. You know that when you have a points on a graph, right? And a graph with an x-axis and a y-axis. Those are actually x, y values. All right, it's not just x only, it's not just y only. So we don't want to just know what x is equal to, we want to know what y is equal to as well. That brings us to the final step. What you do is you pick an equation, any equation you want in the problem that has both variables in it. It must have both variables in it, okay? Because what we're going to do is we're going to plug the x into the equation that we pick, and we're going to solve for y. So it makes sense that you pick something that has both variables in it. You need to have a place to plug in the x, and then you need to have a y to solve for. So I'm going to pick this one right here. Usually that one where you got the variable by itself at the beginning of the problem, that's usually the easiest one, but theoretically, you can pick any equation that you want as long as it has both x and y in it. Okay, now notice that y is already by itself, right? So anytime you're trying to solve an equation where the variable that you're trying to solve for is already by itself, as long as it's not on the other side, you're fine. You just need to do order of operations on the other side. All right. We get 5 plus negative 2, which is the same thing as 5 minus 2, and then that would be 3. So what's my final answer then, you guys? Remember, your final answer is an ordered pair, as if it was on a graph, as if it was an intersection point on a graph. Okay? If these two lines right here were the real lines for these two equations, I'm not saying that they are, but if they were, then this point 1, 3 would be the intersection point, because it is the solution. X equal to 1, y equal to 3. So the way you write out your answer is you put the 1 and the 3 together. Always put the x first, like always, okay, when you're doing an ordered pair. And that is how you solve with the substitution method. Let's try that again. Out of these 4 variables, you guys, which one of them would be the easiest to get by itself? And try to avoid fractions if you can. On this problem, we were able to by solving for this y right here. Here, we do not have a coefficient of positive 1 over here like we did over here. But we do have some coefficients of negative 1. See how that's negative 1y and this one's negative 1x? Okay. Usually when the coefficient is negative 1 instead of positive 1, usually you'll still be able to avoid fractions. Just so long as there's not any fractions before you divide out. Dividing by negative 1 will not make any fractions that weren't already there. All right. It won't create any fractions unless they were already there. And as you see, they won't be. So I could pick either one of these since they both have a coefficient of negative 1. All right, they don't, they're both just as easy to get the variable by itself. Just to be different this time, I'll pick the x since I solved for y last time. It does not matter, though. Okay, it doesn't matter which variable you solve for first in any substitution problem. It really doesn't. So I'm going to get this x by itself. How do I do that? These are linear equations again, right? Okay, all of these are. So again, if you're trying to solve for the variable x, that's your red term. And then the terms that do not have the x in it are going to be your green terms. So we need to move the green terms to the same side by what? By adding or subtracting them over, assuming there's no parentheses, which there's not. Then the x is not completely by itself yet. Okay, remember when you have negative x, that's not by itself. When you have negative x, you got to divide by negative 1. We've seen that before. Okay, in order to get x completely by itself, it's got to be x, meaning positive 1 times x. This is negative 1 times x, so you still got to divide out. How do you divide two terms by just a single term there? Just like we did before when we had mx plus b, if you've got two terms and you're dividing it by a single term, and yes, you have, remember, you got to divide the entire left side and the entire right side. That bar has to go completely across both of these things here. All right, you can't just divide the 10 only or the 3y only. All right, that's how it works when you divide both sides by something. You got to make that bar go all the way across both the left side and the right side. So that reminds us that we've got to divide both of those terms just like I did here. All right, and how do we divide that again? You figure out the sign of each one. Negative divided by negative is positive, so I made this a positive answer right here. Positive divided by negative is negative, so this is a negative answer. That same type of thing is going on here. 10 divided by negative 1 is going to be a negative answer. And we get, I'll simplify that in a second here. Yes, I know that's equal to negative 10. But again, if it's negative, put the minus in front. If it's positive, like we have here, because it's negative divided by negative, then put the plus in front. Okay. But what's important is that both of the denominators are equal to 1. All right, that won't always happen, but in every single time you divide, but it does here. And so that means that we can get rid of the ones when the denominator is 1, and we just end up with this right here. Okay. So divide both of the terms by this. And by the way, when you divide, I kind of made that a little bit more complicated than it needed to be, just because I wanted to emphasize and remind you again about how to divide. But whenever you divide by -1, all it does is change the sign of what you divided into. Okay, so 10 becomes -10. -3y up here becomes +3y. Okay, but I just wanted to make sure you got your signs correct, or you put the correct signs in the front of each term. And so just make sure you're doing that. When you divide two terms by -1, you've got to have a plus or minus in between the two answers, because it still has to be two terms. All right. But otherwise, yeah, when you divide by -1, all it does is just change the signs of the two terms that you have that you're dividing into there. Okay. All right, so we got x by itself. All right. What do we do after we get the variable by itself in the first step? You take this answer right here and you plug it into the what? Into the other equation. It's got to be the other equation. So since I got this answer from the second equation, then I have to plug it into the first. Let's do that. If I had gotten the answer from the first equation instead, like for example, what if I had gotten this y by itself up here at the top? Then you would have plugged in that answer into the second one. It's always the other one on step 2. So plugging it into that top one there, we get this right here. Okay, and we then solve that equation. It's just your normal, regular linear equation with one variable in it. Distribute. Combine like terms. Okay. Move the 70 over with the -10. Okay. Near the end of the prerequisite review packet, we did solving one variable linear equations, if you ever want to review that. But remember, we've been doing them many times throughout the semester. But if you just need to make sure, no problem. Just remember it's near the end of the prerequisite review packet. You'll see it there. And let me know if you have any questions as usual. Once you solve for that variable there, after you plug in on the second step, the third step is to solve for that variable. Okay, that's the once you solve for that variable, whichever one it is, we haven't solved for the other variable yet. Yes, we know that x is equal to this thing, but I actually want to know what number x is equal to. I don't want x equal to something with a variable in it. That's not enough. All right. Once I solve for that variable here, after I plug into the other equation, I now need to solve for the other one. So again, on this step, after you solve for the first variable and you want to solve for the other one, pick an equation that has both variables in it. Any one that you want in the entire problem. But this one's the easiest one because the variable that I haven't solved for yet, which is x, is already by itself. So I don't need to be dividing out or moving terms around or any of that kind of stuff. I just need to plug in the y equal to 3, like this. And then, since the x is already by itself, I just need to figure out what the other side's equal to. Multiplication comes first, then addition. What's my final answer? My final answer is -1 for x and 3 for y, just like that. Okay, so that is the substitution method. Okay, flipping over to the back side of the worksheet. We now are going to be looking at the elimination method, otherwise known as the addition method. Remember, it's the same thing. As we talked about right there, addition and elimination, same thing. What are the steps for solving that? First thing they want you to do, and usually this will already be done, first thing they want you to do is to write each equation with the variable terms on one side and the constants on the other. In other words, get all your x and y terms on one side and the terms that don't have the variables in it, the constant terms, in other words, on the other side. And in particular, because this will make it easier on you, it's not mandatory what I'm about to say, but it will make it easier. Line up the x terms and line up the y terms, line up the equal signs and line up the constant terms. Line up all those things. It's going to make the next few steps a little bit easier for you. All right, now what you need to do, kind of similar to what we did on the front side of the worksheet, what happened when I substituted into the other equation on the step 2 of the substitution method? What happened was one of the variables disappeared. We went from having equations with both x and y in it to just having an equation with just one of those variables in it. All right, so you eliminated a variable. You did it by substitution though. All right, there's another way to eliminate a variable, all right, and that's why they call this the elimination method coming up. It's more the traditional way of eliminating a variable, and that is by adding the equations together. Okay, what does it mean to add the equations together? We'll talk about that here in a second, but we're not ready to do it just yet. There's one additional step we got to do first. All right, but what if I were to add the equations together? What would happen? In other words, if I were to drop the and I'll put it up here because this is not the correct step. I'm just saying what would happen if we did it. If I were to add both sides of the equations together, in other words, if you add the left-hand sides together and the right-hand side together, that's what we're normally going to do. We're just not going to do it yet because it's not going to help us until we do something else first. But if I were to do that, that means to combine like terms. When you add polynomials, you combine like terms, and that's what we're doing here. Wouldn't I get 9x plus 6y right there if I combine like terms on the left-hand side here of the equal sign? And if I combine like terms over here, I get 13. What's the problem with that? The problem is that I did not eliminate a variable. The goal was to eliminate a variable. All right? And so that's not going to, that didn't help us there. There's something that we need to do first. Okay? Now, this particular problem has kind of a weird answer. So what I'm going to do right now is I'm actually going to skip this problem and come back to it in just a moment. Okay. And I'm going to do this one here because this one's not so weird. Okay. It's always good to explain the ones that aren't so weird at first so that you don't get completely thrown off by that. As you guys saw, we combine like terms, right? Isn't it true that when you combine like terms, the terms eliminate if their coefficients are opposites of each other? For example, if I said negative 6x plus 6x right here, wouldn't that just cancel out? And the reason why they cancel out is because the coefficients negative 6 and 6 are opposites of each other. Okay, that's exactly what you want to have happen. For example, this is negative 2y right here, right? Okay, if I can make that positive 2y, I can then make them eliminate or cancel out when I actually add the equations together, kind of in the same way I added the equations together over here. All right. So how do I change that from y to 2y? What you do is, as it says here in the second step, we already made sure the first step was done with the variable terms on one side. It says multiply one or both equations by appropriate non-zero numbers, and they've got to be constant numbers. Don't multiply by variables. Okay. Appropriate constant numbers if necessary. Usually it will be necessary. So that, and this is the important thing, so that the coefficients of either x or y, your choice. You could do either x or y. It does not matter which one. It really doesn't. Okay, so your choice, so that they are opposites of each other. Just like the negative 6 and 6 are opposites of each other. One is positive 6, one is negative 6. That's what I mean by opposites. Same number, different sign. Okay, so in other words, you guys, I could multiply 2 times the first equation. I'll call it E1 for short. I can multiply 2 times the first equation, and then after I multiply that, I can then add it to the second equation, which I'll leave unchanged. That will then make these opposites of each other. What if I had wanted to eliminate the x instead? You could have done that. You could have multiplied this one by negative 4. Because then that would have made this 1x times negative 4 would have been equal to negative 4x. That would have then canceled with the 4x right here. But the thing you really got to remember, though, is you can't just multiply the term that you want to change and then just ignore the other terms. No, no, no. If you want to multiply part of an equation by something, you have to multiply the entire left side and the entire right side. You can't leave anything out. Okay. If both sides if you have a linear equation with no parentheses like we do on all of these problems here, the way to multiply both sides entirely is simply to distribute the number that you're multiplying to each term, keeping the equal sign in the same place, though. Okay, and then if you have more than one term on one side of the equal sign, if you got two terms, for example, you got to still have two terms when you're done distributing. So remember to put a plus or minus in between. We'll do that. So what do we get if I distribute that 2? I get 8x plus 2y. It's positive 2y, but I got to have a plus or minus in between. All right, since just like when you distribute with parentheses, all right, you got to have pluses or minuses in between the answer when you have like 2 times a parenthesis with multiple terms in it. It's the same idea here, all right. Got to have pluses or minuses in between. Keep the equal sign in the same place. And then 2 times negative 23 is negative 46. I'm going to keep the other equation exactly the same. And what does this give me here? Now I do the same thing that I did over here before I erased it. Now I what? Now I add the left sides and I add the right sides together. What's going to happen when you combine like terms, which is what you do when you add the two sides together, okay, but keep the two sides separate. The equal sign is like a separating bar right here, okay. Just combine the left sides and combine the right sides separately. The y's cancel, though, when you do that, and so we're left with 9x equal to negative 63. And we eliminated a variable, didn't we? The y is now gone, and so just like in the substitution method, after you eliminate one of the variables, you then solve for the other one. All right, just like we eliminated a variable when we plugged it into the other equation in step 2, the step 2 part of substitution, we then solve for the variable that was still left over. Same exact thing right here, only it's a lot easier here because you just have a single variable term and a single constant term. When you have a linear equation, as we've said many times before, where linear equation, single variable term, and that's it on one side, single constant term, and that's it on the other side, that's the division step. Nothing else you need to do. And we get x equal to negative 7. What did we do in the substitution method after we solved for one of the variables? We then went back and picked any equation that we wanted to that had both variables in it, okay, and we plugged into that so that we can then solve for that. Solve for the other variable, pardon me. Just like we did in the substitution method. I'm going to pick this one right here. But you could have picked any one of the top 4 equations here because they all have both variables in it. Just don't pick this one, all right? Don't pick one that has only one variable. So I'm going to go ahead and, like I said, pick this equation right here. Any equation with both variables in it will do. Plug in the negative 7 right there. First thing you need to do anytime you plug a number into a polynomial equation is, and I say polynomial equation because this is a polynomial right here. It's just 2 terms being subtracted. All right, no parentheses. It's just a polynomial. If you plug if you have a polynomial on one side of the equation and you plug a number into one of the terms, figure out what that term's equal to first. Okay. This is 1 times x that you plugged into. So that's 1. You don't have to write the 1 right here, but that's 1 times negative 7. So that is just negative 7 right there. Okay. All right, so figure out what that term is equal to first, and then now it looks just like a normal equation. You don't have like a number times a number. You don't normally see that in an equation. You might have a number times a bracket with 2 terms in it. You see that, but you don't see this. Figure out what that term is equal to, and then proceed from there. This is a normal-looking linear equation where you need to get the two terms that don't have the y in it on the other side from where the y term is. So I get negative 2y equal to negative 10. And then I divide out to get the y completely by itself, and we end up with y equal to 5. So just like in the substitution method, we end up with, we solve for x and we solve for y, not necessarily in that order. Sometimes the y gets solved for first, but we solve for both, and then we put it together as an ordered pair. X always comes first. Okay? And so let's bounce back over to number 3 now. What could I, usually when I try to figure out what to multiply by, I look at the bigger number. Like let's say I wanted to eliminate x this time. You could do y again if you want, but let's say I want to eliminate x. Yeah, I usually look at the bigger number, irregardless of whether or not it's positive or negative, just the bigger number. And I say, what could I multiply the smaller number by to get it to be the opposite of the bigger number 6? All right, well, we know that 3 times negative 2 will make it the opposite of 6 right there, right? So I'm going to multiply negative 2 times the first equation, all right, and that will make these the opposite. So what happens if I do that? Again, if you're multiplying both sides of an equation when it's a polynomial equation, with no parentheses, just terms being either added together on one side, normal monomial terms, or just a single term like on this side, what you do in that case, I'm not talking about when you got radicals in your equation or fractions or logarithms or, you know, those the variable and the exponent. No, just normal terms, all right, that we reviewed at the very beginning of the prerequisite review packet, those kinds of terms. That is, again, when you distribute to each term here, keeping the equal sign in the same place, just like in the number 4 over here. We get what? We get negative 6x minus 4y. Keep the equal sign in the same place, and then we got negative 10. Keep the other equation the same, because we want it to be the same. We want the negative 6 and 6 to be opposites of each other. So don't mess with that 6 down below here. We want it to be the opposite of negative 6. Then what do we do after we get the one of the variables opposites of each other? Okay, we then add the two sides of the equation together. But something funny happens here, as I promised you. Sometimes when you are in the process of trying to get one of the variables to be opposites, you end up making them both the opposite. That happens sometimes, all right? You meant to just try to make one of the variables the opposite, but then the other one just ends up being opposite at the same time, negative 4 and 4. Don't be alarmed by that. I'll show you how to handle that. But what happens when you combine like terms on one side of the equal sign and all of the terms cancel, what does that mean? It means that it's equal to 0. If all the terms cancel when you are combining like terms, it's equal to 0. And then this is equal to negative 2, isn't it? What happens, and we've seen this before, not in the same kinds of problems, but it will end up being the same result in this particular case. Let me just show you a visual of that. It was actually near the end of the prerequisite review packet. What happens when the variables disappear while you're solving and you get a false statement? Because 0 and negative 2 are not true. They're not equal to each other. This is a false statement right here. Okay. As it says right here, if the variables go away while you're solving, see how they canceled out right there? And you got a false statement, 20 and 21 are not true, not equal to each other, that's no solution. Same exact, even though this is a different kind of problem, it's a system, it's still going to be that same result. Okay, remember I said earlier, sometimes when you solve a two-variable, two-equation system, you get no solution, and we implied that meant that it was parallel lines. Well, that's exactly what these two lines must be then. If I were to graph these two equations right now, you would get parallel lines. So it makes sense that there would be no solution because there is no intersection point. And that's problem number 3. All right, you guys, moving on to number 5 right here. Normally, I would take the 2 and multiply by -2 so that I can get 4 and -4 right here. But I'm going to intentionally, because it's going to help us later when we absolutely are going to have no choice, I'm going to eliminate the y's right here. And I know you might be thinking, why would you do that? Because how do you multiply by 3 in order to make it equal to -5 so you can cancel it with the 5? In other words, what do we usually do? We usually multiply by the smaller number to make it the opposite of the bigger number. Okay? Well, there are some problems where both x and y are like this, where you can't just multiply by one number unless it's a fraction in order to make it the opposite of the other one. So what you do in that case, that doesn't mean that you can't do it. It doesn't mean you're even going to have to use a fraction. What you can do, if you can't easily find a number to multiply by one of the equations to make it the opposite of the other one, what you do instead is you take both numbers, write them off to the side over here, but I'm going to flip them. It's not a fraction, I know, but we're flipping them anyway, all right? I'm going to flip the coefficients, and then you change the sign of one of them. Only one of them. If you change the sign of both, it won't work. And then what you do is you multiply the two equations by those two numbers respectively. -5 times the first one, 3 times the second one. What ends up happening if I do that? You end up getting -15y on the first equation. And then you get +15y on the second one, just distributed in the same way we did in the last two problems. Okay, so this is something that we sometimes have to do if you cannot just easily multiply by one of the equations in order to get the opposite terms, the opposite signs like we did in the first two problems, all right, when we just had to multiply by one equation here and we got the opposite signs that we wanted, all right. There will be times in 5.2 where it'll be very much to your advantage to, in fact, there may even be some cases where it's absolutely necessary that you know this strategy here where you got to multiply by both equations. So again, what did we do? And you could have done this with the x's as well, although it would have been unnecessary, but you flip-flop the coefficients off to the side, not in the problem, keep the problem the same, but off to the side, you flip-flop the coefficients, and then you change the sign of one of them. That way, it'll end up being opposite sign if you change the sign of one of them. Let's go ahead and distribute this out. We get -20x minus 15y is equal to 5, and then the other one is going to be 6x plus 15y, so you can see the y's are going to cancel right there, and then we got 9. So then we, after we make the coefficients opposites of each other, we now add the two sides together. We get -14x equal to 14. The y's cancel out. I then solve that resulting equation like we talked about in the previous, or in the problem number 4. After you add the two equations together, it should eliminate a variable, thus the name elimination, and then it creates an equation with only one variable left. You then solve for that. I get x equal to -1. And what do we do after we solve for one of the variables, you guys? We then go back and we plug it back into an equation that has both variables in it. All right. And I'll go ahead and pick the second one here. That's fine. Okay. All right. Remember to figure out what the term is equal to that you plug the number into. It is equal to -2, as you can see there, 2 times -1. And then I solve as normal here. So since it's a linear equation, I get the two terms that don't have the variable in it on the same side. I then divide out, and my final answer for the y part is going to be y equal to 1. So what's the final answer here? -1, 1. Okay. All right, so that's number 5 right there. What happens when you have number 6 right here? That's also going to be a unusual answer. What was the one that we haven't seen yet? We've seen a lot of problems where there was one solution. We've seen a problem where there was no solution. We haven't seen this one yet. That's what's going to happen here. Let me show you why. Again, you can get away with just multiplying by one equation this time, or multiply by one equation this time. Look at 3, for example. I can multiply that by -3 to make it the opposite of this, right? So you can keep the 9 the same. In other words, just multiply that one by -3, and that will get the job done, won't it? Okay. And so if I distribute that through here, and by the way, you could have done that same thing with if you wanted to eliminate the y's, all right? You could have multiplied, interestingly, by that same number, and that would have given you -15 and 15. Anyway, what do we get here? We get -9x minus 15y is equal to 6. On the other one, we get it stays the same. Okay. And just like in problem number 3 up here, all right, sometimes when you go through the process of eliminating one variable and making it the opposite sign and all that stuff, you end up with the other variable also turning into the opposite signs as well, -15 and 15. If I then combine like terms, both the x's and the y's will eliminate, and every single term on the left side of the equal sign cancel out. And when every single term on one side cancel out, that side is equal to 0. But what's different about this problem is that the other side also is equal to 0. All right? Now, we saw this kind of thing again back in chapter 1 when I showed you earlier about when it was no solution. If it was true after all the variables go away, then we said it was all real numbers. That is not the case here, but it is something similar. Okay, remember, all real numbers, that's a lot of answers, right? That's actually an infinite amount of answers. So it would make sense that when the variables go away, as you can see right here, when the variables disappear, and you get a what? You get a true statement, 0 and 0 are truly equal to each other, as opposed to these two numbers which were false because they're not equal. When that happens, then it's the situation where it's the same line and you have an infinite number of solutions. Now, that's not the answer you give. That's just the type of answer that you have. It is an infinite number of solutions, but how do we write out the answer? When you got one of these two variable, two equation systems and you get an infinite number of solutions, here's how you got to write it out. Listen closely. It's kind of complicated, but we'll get through it here. What you do when this happens is you pick an equation. It does not matter which equation you pick because the two equations in this problem, remember, they represent the same exact line, and so the equations are equivalent. So no matter which one you pick, you'll get the same answer. So you pick an equation, and then you pick a variable in that equation and solve for it. Just like you do on the first step of the substitution method. Okay. Again, you only do this when you have an infinite number of solutions. So, if I do that, I'll go ahead and pick the very first one up here. It does not matter. You could pick any of these four. It'll give you the same answer as long as you're solving for the same variable. If you pick the other variable, it'll look a little bit different, but both answers will be acceptable, as I'll explain here in a minute. I'll go ahead and pick x right here. So I'm going to solve for x right here. Yes, I know it's going to give me fractions. All right, but that's okay right here because we're at the final answer. It's okay to have fractions. I just didn't want you to end up with fractions at the beginning of the problem, and that's why we try to avoid fractions in other situations in this worksheet. All right, it's because you don't want to be carrying fractions throughout the entire rest of the problem. But since we're at the end of the problem, fractions are no big deal. That's okay. So how do I solve for x? Since it's a linear equation with no variables in it, or sorry, a linear equation with no parentheses in it. There we go. All right, linear equation with no parentheses in it. Kind of had a brain freeze right there. Sorry about that. Then what do we always do? We take the term with the variable in it that we want to solve for. That's in red. And we get the other terms, which I put in green, that don't have the variable in it. And we put it on the other side by adding or subtracting it over, in this case subtracting. And then you divide out the 3 to get the x completely by itself. So what does all this mean? Okay, this is where it gets interesting. Listen closely here. So what I do is this. We write a general ordered pair right here, and it's the variable that you did not solve for. Remember, we solved for x right here. The one you do not solve for, I want you to write that where it belongs here. Since y always goes second, put it in the second spot after the comma. And then since x is equal to this fraction, you put that first where the x normally goes. What does this mean, though? I mean, what is the purpose of this? Okay, this means this. Y could be any number. And you don't need to write down the words any number here. You could just circle this, all right? And that's fine. But let me show you what it means, though, so that you know what you're writing. This means that any number in the world can be... Sorry, that fell off the screen there. Any number in the world can be plugged into here, and it'll give you a solution. Okay, if I plug in 1 into here and then into here, it gives you these two numbers with the comma in between it that forms an ordered pair. For example, if I plug in y equal to 1, I get negative 2 minus 5 times 1 over 3, which is negative 7/3, comma 1. You don't have to write that down. I'm just saying that that's what it would give you. So negative 7/3, comma 1 would be one of your solutions. If I plug in y equal to 2, I would get... what would that be? That would be negative 12 over 3. And so that would be negative 4, comma 2. All right, so any number in the world can get plugged into here, and it would be a solution. Since there's an infinite number of numbers in the world, and every single number would work when you plug it in here, that's why we have an infinite number of solutions. But that's what the solutions look like right there. Okay. If you plug in every number in the world into here and you create an infinite number of ordered pairs, those ordered pairs are in your solution set. Do I have to solve for x? No. Suppose I wanted to take an equation. I'll just pick the second one this time just to be different. It's going to give you the same answer, so it doesn't matter. It won't be the same as this one, but it'll be the same as it would have been if you had picked a different equation. But I'm going to solve for y this time. So if I solve for y this time, I get, again, y. The y term is the red term. And so we need to move the... terms that do not have the y in it to the opposite side of where the y is, like that. And then you need to divide out to get the y completely by itself. Again, it doesn't matter if you put the variable term first right here. We're not trying to do lines right now or anything like that. We're not trying to graph lines. So what do we get here? Again, the variable that you did not solve for, we solved for y, so I'm talking about x here. Put that in there. Just say x in the first spot where the x belongs. And then since y is equal to this fraction, you then put the fraction in the y spot. So whatever you solve for, put that fraction that that variable is equal to into its respective spot. Y, if it's y, you put in the second spot. If it's x, you put in the first spot. And then just put a general variable in the other spot. Again, what this means is that any number could go here. And believe it or not, you guys, if you plug in every number in the world into this spot and that same one into this spot, it will actually generate the same order of pairs that this one does. I know it looks completely different, but in the end, it would. All right? And so both of these answers are completely equivalent, and therefore they're both correct. Again, you only do this when? You only do this when you got an infinite number of solutions. When you have an infinite number of solutions, it's when the variables disappear while you're solving and you get a true statement. All right? If the variables disappear while you're solving and you get a false statement, that's much easier. You just got to say those two words right there. And if the variables don't disappear at all, then you just get one x value and one y value, just make it into an order pair and then circle that. Again, this is just for the two variable, two equation systems that we're talking about right now. Okay. One last thing I wanted to point out here before we're done with all the problems, but let's say, for example, that, see how right here I solve for x? What if I had solved for y first and I ended up getting y equal to 1? I want to talk about that, but that, you know, that's actually not a good example. Let me, you know, actually, no, that's okay. That's okay. That'll still be fine. So let's say I solve for y first, all right, and I plugged it in. Remember, after you solve for one variable, you got to plug it into any equation that has both variables in it. Doesn't matter if you're doing substitution or elimination. For the purpose of figuring out what the other variable is then equal to. So let's just pretend like we solve for y first. I want to show you something here. If I did, and I'll write this down here because this is the, we're already done with this problem. This is just a separate thing that I want to make sure you understand. Because you could run into this situation in some problems, either in this section or in a future section. If you plug a number into the second term on that side of the equal sign, see how I plugged it into the second term right there, not the first one this time? Again, you still figure out what the term is equal to that you plugged into whenever you plug a number into a polynomial. You still do that, but remember, you guys, when you do that, please remember that whatever you end up getting, make sure there's a plus or minus in front of it. These still got to be two separate terms here. And so if you do 5 times 1, that's equal to 5, right? But I don't just say 2x5. I've got to put either a plus or minus in between that. What do I put there? It all depends on what your answer is. Since it's positive 5, I put a plus there. If this had been 5 times negative 1, then that would have been negative 5, and then I would put minus right there. I would say minus 5. All right. And one other note, if this had been negative 5 right here, remember to multiply the entire thing by whatever you plugged in. Okay? Because then the negative would be part of the coefficient there. But whatever answer you get, if it's positive, put a plus there when you plug into the second term right there. And then when it's if it's positive, you put a plus there. And if the answer had been negative, you'd put a minus there. All right. And you'll see that we end up getting the same answer here. If I move the 5 over and then divide out, it gives me that same answer that I had up here, negative 1. Okay. Not that we didn't already know that, but I just wanted to finish that off. Okay, so that second term can be kind of tricky. So I just wanted to make sure that you were okay with that. But as usual, let me know if you have any questions. All right, it's going to be important to understand this section because the next section is much more complicated. Believe me. So let me know if you have any questions at all, so that we can get everything all squared away before we go to that next section. Okay, but that's it for section 5.1. You have a good day, and we'll see you next time. Take care.